We have to prove by mathematical induction that 2 plus 4 plus 6 plus all the way until the last term is equal to n times n plus 1. So the first thing that you want to do, you want to write out P1 statement, PK statement, and PK plus 1 statement. P1 statement basically means the n value will be 1. So you're talking about the first term because there are n terms here on the left side. There are n terms. Now notice that 2n makes sense with any of these numbers that you choose. So for example, if n is equal to 1, you're talking about the first term. 2 times 1 is indeed 2. If you're talking about the two terms, or try to find the second term, you're going to have to use the n value of 2 for this. 2 times 2 is 4. If you're setting the n value of 3, it's going to be 3 times 2, which is 6, right? So the n is the term number, all right? Because there will be n terms on the left side. So P1 basically means you're taking the first term, right? So it's going to be 2 on the left side is equal to, and you're going to substitute the n with 1, right? Because P1, you're talking about the n value of 1, right? So 1 times 1 plus 1. And we're not going to verify this. We're just going to write these out. PK statement. PK statement's easy. You just substitute the n value with k. So it's going to be 2 plus 4 plus 6 plus all the way until 2k is equal to k times k plus 1. And now the pk plus 1 statement is just basically going to substitute this k value with k plus 1 because k plus 1 is the last term. So it's going to be 2 plus 4 plus 6 plus all the way until 2k plus first term is equal to k plus 1 times k plus 1 instead of the k here, plus 1. Okay, so these statements are written out, these three statements, P1, PK, and PK plus 1. Now we have to show P1 being true. P1 is true. And verifying that because 2 is equal to 1 times 2, right? 1 plus 1 is 2. So it's 1 times 2, which is indeed 2. So we showed that the P1 statement is true. Now, assume that PK statement is true. We don't need to prove it, we're just going to assume it. Okay, we're going to assume it. Assume that PK is true for arbitrary k value. Then, so assuming PK is true, we're going to basically need to show that PK plus 1 statement is true. If we show PK plus 1 statement true based on the assumption that PK is true, then that's enough to conclude that the Pn statement here is true for all n. Okay? So basically, what that does, PK plus 1 statement becomes the following. We start with 2, 4, 6 until 2k. But here's what we need to do. We need to basically add one more term, right? Because PK statement ends with a 2k, but PK plus 1 statement will need to be ending with 2 times k plus 1. Okay? And that is equal to, we can copy the right side, k plus 1, and we can simplify this, k plus 2. Okay, k plus 1 is equal to k plus 2. So now, what needs to be done, we need to compare this statement with this statement. Notice that they're almost the same, they're similar in fact, except that this term is absent on the left side here. Everything to the left of this term is exactly the same. It's identical to this left side. Okay, so we can say so that if we add this on both sides of pk statement, we will basically show the left side to be exactly this. We will show the left side to be exactly pk plus 1 statement left side, and we will need to add this to this side. Okay, so basically what I'm going to do, I'm going to write this statement. I'm going to write this statement, pk statement left side. And I'm going to add this guy. I'm going to add this guy to this side. But I have to do the same thing on the other side of pk. Right? And I'm going to just do it like this. I'm going to show this with red because we're adding it to both sides. Okay, we're adding this to both sides. And now what needs to be done is that we have to show that this right side turns somehow into this side. Because if we do, we already made the left sides look exactly the same for pk plus 1 statement. Right? Because our mission is to show that this pk plus 1 statement is true. So our mission is to make sure that this left side is indeed equal to this right side, right? Because right now it's an assumption only, but if under the assumption of pk being true, we show that these two are equal, these two sides, then indeed pk plus 1 is true. But for now, it's only an assumption. We need to prove that, right? So we need to make this side turn into that side. Which means, now I'm not going to say which means, I'm going to say the right side. So I'm going to write pk plus 1 because this is indeed pk plus 1 statement, allegedly pk plus 1 statement, until we show the right side being the same as this right side. Right? The right side is then what? K plus k plus 1, let's copy this down, plus 2 times k plus 1. And notice these two are the same factors. They both multiply k and positive 2. So we can group together the k and positive 2 like this. And then they will both multiply k plus 1, right? Because this is algebraically possible, right? You can think of it as factoring by grouping step that we've done. So what does that tell you? It tells you that, look at this, these two sides are identical now. These two sides are identical. So, which means that copying this left side, 2 plus 4 plus 6 plus 2k plus 2 times k plus 1 is equal to this. K plus 2 times k plus 1, which is the same. The order doesn't matter. K plus 2 times k plus 1 is the same as k plus 1, k plus 2, right? So I can just write it like this. K plus 1 times k plus 2. Right? Multiplication is commutative. You can switch the order of the factors. It doesn't matter. Right? So what this tells you, this is precisely the statement for pk plus 1, because we showed this right side being equal to this, which is equal to the original that we assumed, right? So we indeed showed that this left side is equal to this right side, right here, by first adding 2 times k plus 1 to this statement left side. And we had to do the same thing on the right side, which we did here, right? So this is just a series of steps that you have to do to show this is the induction step. This is the complete induction step when you begin adding the k plus first term to the pk statement left side and also the right side. This is the complete induction step here. So as a result, we show that this is being true since we can say, which means that this statement holds true, right? Because we showed it holds true based on the assumption that pk statement is true, right? So that holds true. Thus, pk plus 1 statement is true by principle of mathematical induction. Pn statement holds true for all n. So once you complete the induction step here and you showed that the right sides match after doing some algebra, you will be successful. You will have shown that pk plus 1 statement is indeed true. Thus, the original Pn statement is true for all n. So thanks for watching. I hope this was helpful. See you in the next video.